Great. Hello, everyone. I'm Kaimei. I'm a professor at the University of Washington, and it's my pleasure to be the host for today's Northwest Quantum Nexus seminar speaker. Before I move on to introduce Professor Edo Waks, I first want to mention a few things regarding the Northwest Quantum Nexus seminar. The seminar is being recorded. By attending this meeting, you may appear as an attendee in the recording. Your questions and comments in the Q&A will also be part of the recording. Also, the NQN has a code of conduct. The NQN is dedicated to providing respectful, friendly, professional experience for everyone, regardless of gender, sexual orientation, physical appearance, age, race, or religion. We do not tolerate any behavior that is harassing or degrading to any individual in any form. Individuals are responsible for knowing and abiding by these standards. We encourage everyone to assist in creating a welcoming and safe environment. NQN reserves the right to refuse admittance to or remove any person from any event at any time at its discretion. Okay. So today's seminar speaker is Professor Edo Waks, who is in the Department of Electrical and Computer Engineering at the University of Maryland in College Park. He is also a member of the Joint Quantum Institute, a collaborative effort between the University of Maryland and NIST, dedicated to the study of quantum coherence. Edo received his BS and MS from Johns Hopkins University and his PhD from Stanford University. He is a recipient of the Presidential Early Career Award for Scientists and Engineers, an NSF Career Award, and an ARL Young Investigator Award for the investigations of interactions between quantum dots and nanophotonic structures. His current work focuses on coherent control and manipulation of semiconductor quantum dots and their interactions with photonic crystal devices for creating strong atom-photon interactions. Today, it's a pleasure to welcome him to share his recent work on quantum photonic simulators. Thank you, Edo.
Thanks, Kaimei, for that wonderful introduction. I'm going to share my screen now. And before I start, I just want to confirm that you're seeing my intro slide.
That's correct.
Great, thank you. Okay, I want to thank the organizers for inviting me to speak today about some of the work we've been doing towards strongly interacting photons in synthetic dimensions for photonic quantum simulation. This work was done by myself and my close collaborators at the University of Maryland College Park and the Joint Quantum Institute. So I'm sure that many of you have heard all the hype about quantum computing and how rapidly it's been progressing to date. And indeed, there has been a lot of spectacular progress recently, from demonstration of quantum supremacy by Google to IonQ recently doing a SPAC merger, making them the first quantum company to be publicly traded on the New York Stock Exchange. And there's also been rapid advancements in the number of qubits that quantum computers are starting to contain. But despite all this progress, I think it's pretty safe to say that we're still far away from what one would call a digital quantum computer. This is a quantum computer that's gate-based, that does fault-tolerant, error-corrected quantum computing, which is what we all dream of. We simply don't have the technology to date to do it, and it's not probably going to happen in the foreseeable future. What we do have in the near term are what I would call quantum analog computers or quantum simulators. These are special purpose computers that are built to solve a specific problem. And usually this is some sort of physics problem that is hard to calculate, but it doesn't have to be, or it could be a molecular reaction. It could be any kind of quantum problem that we simply don't know how to solve with a classical computer. And here are some three very nice examples of recent demonstrations of quantum simulation with up to in this case, up to 256 qubits. So the question that I'm posing is, and I'm sorry for the misprint here, this should be simulation, the title, can we do this with photonics? And it would be great if we could, because photonics gives us a lot of things that are hard to get with other systems like trapped ions and microwaves. We have single particle preparation and measurement. We can operate at ultra high bandwidth, and we can implement these quantum simulators using scalable and well-established photonic technology. For example, integrated photonic circuits that can pack a tremendous amount of components onto a chip, or fiber optic components that we can buy from standard telecom technology, which is extremely mature and well developed. So this would be great to do, and indeed, many people have been thinking for a long time about how photonics can be used for quantum simulation. And here are three nice examples of things that people have done, simulated using photonic systems. Here's an example of simulation of molecular orbitals of benzene ring using lasers and wave interference. In the area of integrated photonic circuits, people have looked at things like Anderson localization caused by disorder after you scatter off of many different beam splitters with different splitting ratios. And more recently, we've seen the emergence of topological photonic devices that create a photonic analog to topological insulators and quantum Hall devices. And these are done, in this case, this was done through using a silicon photonic circuit that was foundry fabricated. So there's lots of ideas about how we can use photonics to do quantum simulation. And one of the basic fundamental primitives of all of these simulations is the random walk. So in fact, it's not obvious, but all of these quantum simulations are just forms of quantum random walks, where you have a walker, in this case a photon, that can randomly jump from from one side to another in discrete time steps, and this is repeated. The difference is that because the random walker is a quantum particle, it can undergo many trajectories, and that creates interference. In the case of multiple particles, it can also create multi-particle interference. And this has been used, this type of random walk has been used to simulate lots of physics. I already showed you the topological, the topological insulator with edge modes. This is work from Hafezi that actually use these integrated photonic silicon photonic circuits. There's also been work on one-dimensional multi-particle transport in one-dimensional random walks with multi-photon interference. Generally, these random walks can implement a broad range of lattice models, and also if you can create interactions, you can implement Hubbard models. If you're willing to work harder and really engineer the walk well, there's a very famous result by Andrew Childs that shows that you can actually do any general Hamiltonian simulation. So by simply creating the right type of random walk and the right unitary transformation after each step, you can do arbitrary Hamiltonian simulation. And in fact, not only are you limited to simulations, you can also do more advanced quantum computational tasks such as quantum search and even universal quantum computing, although I have to say that this requires a kind of engineering of the quantum walk that is very difficult and probably beyond our current capabilities. So the random walk is a really important primitive, and which is why many of the photonic quantum simulators have focused on it. But all of the past implementations have typically suffered from two important missing ingredients. The first is the ability to apply external forces onto photons. Photons don't have mass and they don't have charge. So there's no way to, apply a force onto them, and that's problematic. For example, if you want to study quantum Hall physics, you want to apply a magnetic field that applies a Lorentz force onto the transport of the particles. And if your particle has no charge, you can't apply a Lorentz force. So how do we get around that? The second problem, which is even more difficult, as I'll describe later, is the lack of photon-photon interactions. And so we can study a lot of single particle transport in quantum photonics, but it's very difficult to get to the multi-particle interacting regime where you get many body systems, and you get really interesting many body physics that starts to get into the regime where you're studying things that you cannot compute with a regular computer. So this is a very important missing piece that we have to address. And in this talk, I want to discuss how synthetic dimensions can help us to solve both of these problems. And so I'll begin by discussing what synthetic dimensions are and why they're useful. And then I'll describe how we can use synthetic dimensions to easily apply electric and magnetic fields. In other words, to easily apply external forces onto photons. I'll then discuss how synthetic dimensions can help us to achieve random walks with photons that are strongly interacting using technological capabilities that are currently available. So let me begin by first explaining what I mean by the synthetic dimensions. So typically, when we implement random walks, we usually do that walk in real space. A classic example is the so-called photonic Galton board, which is an array of beam splitters. And you start with a photon, and each beam splitter randomly sends the photon either to the left or to the right. And that action of reflecting or transmitting is equivalent to the walker taking a step to the left or a step to the right. So as you start to walk along the photonic Galton board, you basically start to you basically walk through the random walk in space, and the longer you walk, the bigger the device gets. Another option, which is really Another option, which is related, is the continuous random walk, where you have coupled arrays of waveguides. Similar idea here. You start the walker in one waveguide, and due to evanescent coupling, the walker will tunnel to adjacent waveguides, implementing a continuous time, one-dimensional random walk. But again, the longer we walk, the bigger the device has to get. And the problem with this is that in order to implement these random walks, we need a lot of components. Even in one dimension, we basically need a two-dimensional array of beam splitters. And then if you want to go to 2 dimensions, you now have to create 3-dimensional photonic devices. You need 2 dimensions for your walking space, and then a 3rd dimension for time. And if you want to go to 3 dimensions, you're simply out of dimensions to work with. And so working with physical spatial dimensions is very limiting and results and necessitates very complex devices with many, many components. So the solution is not to use space, because photons have many other dimensions that we can use, many other parts of the Hilbert space that are not spatial but are just as good. For example, frequency. We can have photons that are partitioned, that are partitioned between frequency combs instead of spatial dimensions. For example, in a ring resonator, we can use the different longitudinal modes of the ring resonator as 1 dimension, and maybe space as a 2nd dimension. So this is an example of one of the early proposals by Shan-Wei Fan's group, where they use a linear chain of ring resonators to create actually a 2-dimensional random walk, where one of the dimensions is a real dimension, space, and the other dimension is frequency, which is a synthetic dimension. Another alternative is orbital angular momentum. This was studied also by a number of groups. It's a perfectly good alternate dimension to use. Here we're using the Gas-Laguerre modes. You can argue that that is kind of related to spatial dimensions, and that's fine, but still it can be a very compact space to work with that is more efficient than real space where you're walking between different lattice sites. But the type of synthetic dimensions that I'm going to focus on in this talk are called time-multiplex space. In other words, here, the Hilbert space we're going to use is time bins that denote the arrival time of the photon on a detector. The nice thing about time-multiplexing is that it can implement random walks with extreme efficiency. For example, I can implement a 1-dimensional random walk with only a single beam splitter, and this is how it works. Instead of using this quantum Galton board that I showed you before that required a 2-dimensional array, I simply use a single beam splitter and 2 delay loops. One of the delay loops is slightly delayed relative to the other one. We initiate the photon in one of the loops, and then the beam splitter will randomly partition the photon into either the short or the long delay. After a round trip, the beam split beam splitter will again partition the photons. Now you may have the photons showing up at an earlier time or a later time, depending on whether it took the short delay or the long delay. And this is equivalent to taking a step to the left or to the right. And as you keep on going round and round, you implement this quantum random walk in where the number of steps is determined by the number of times your photons have gone around the loop. And then, of course, we need a way to extract these photons. This can be done actively with a switch, where we allow the photons to go around a deterministic number of times and pull them out with a switch, or it can be done passively with a beam splitter if we're willing to tolerate loss. Either way works, and it really depends on how much loss you can tolerate and how good your switch is. So this idea has actually been experimentally demonstrated originally by the group of Christine Silberhorn and Paderborn, and it can also be extended to beyond one dimension, to higher dimensions. The idea here is to simply, it's basically identical to how you take a matrix and basically unwrap it into an array. So each row of the matrix gets concatenated with the next row. And then we can use a short time delay to implement hops along the x-axis and long time delays to implement hops along the y-axis. And now we have, using basically 2 loops instead of 1, we are able to implement a 2-dimensional random walk. And this was also done a while ago, again, by the seminal work of Silberhorn and the Paderborn group. They implemented a 2-dimensional random walk using only 2 nested loops rather than a complicated 2-dimensional photonic circuit. So this is a really compelling platform to use, but the next question is, how do we apply external forces? And so that'll be the next part, is how do we add these external forces to our random walk with in synthetic dimensions? And the nice thing is that we can do it very easily just by implementing phase modulators. These phase modulators within the loops apply different phase shifts depending on which step the walker is taking, and that creates gauge fields. And gauge fields correspond to forces, either electric or magnetic forces on the photon. And so this is really interesting because it means that we can actually create gauge fields using only loops with modulators, phase modulators in them. This is our experimental setup. When I show you the experimental measurements, this is what it looks like. It's very simple. It's just fibers and then phase modulators. And it fits out in a very simple setup, and it's very easy to put together. It only took a few weeks, and we were running. So this is a really easy way to apply external forces in a random walk. And the first example I'm going to give is how to create a magnetic field. So how do we create the way we create a magnetic field is based on this really interesting idea that was originally proposed by Mohammed Hafezi. You use the following phase convention for your walks. You apply phase shifts when the walker walks in the plus minus x direction, but not when they walk in the plus minus y direction. Not only that, because we have independent control of the phase that the walker undergoes when it walks to the left or to the right, we can apply different phases to those situations. So we can apply a positive phase when they walk to the left, a negative phase when they walk to the right, and we can also scale that phase by the y coordinate in such a way that if the walker goes around a plaquette in the clockwise direction, it will pick up a pi phase shift. But if it undergoes a plaquette in the minus y direction, it'll undergo a negative phase shift. And this is the classic hallmark of a magnetic field. It's basically, this is the one way, this kind of an Aronoff-Bohm phase that you pick up. And the nice thing about this is that we can implement this real breaking of time reversal symmetry without the need for gyrotropic or Faraday materials, which is what would normally be required if we wanted to do it in real space. In real space, we have to break time reversal symmetry for real, and that's very hard to do. Here, because we have independent control of all the phases that the walker has, regardless, either going to the left or right, we don't need any special materials. We just need to program it into our phase modulator. So what does the random walk look like when you implement this kind of phase? Well, let's first look at the band structure when you don't have a magnetic field. The band structure features a Dirac point with ballistic-like transport near the right at the Dirac location, and because of this, as you step in time from step 1 to step 5 to step 9, the random walker ballistically diffuses. This is, by the way, experimental measurements that were done using this really simple fiber setup that I showed you before. Now we just plug in a gauge field by programming our phase modulators using an arbitrary waveform generator. And we do it in such a way that we create a magnetic field which results in a band structure that starts to have these Landau-like levels. So we have this kind of expected behavior that when you have a magnetic field, the bands flatten, and because of that, we get magnetic confinement. The particle doesn't diffuse as much because it's confined by the magnetic field through slow group velocity. Now, with just a little modification, we can create an interface between two regions where we create a positive phase shift, which corresponds to a positive magnetic field, and a negative phase shift, which corresponds to a negative magnetic field. And at this interface, what you observe is the existence of these robust edge, topologically protected edge states. And indeed, this is exactly what we observe experimentally. This is the calculated band structure, which shows the emergence of these edge states between the Landau levels. And if you measure, if you do the experiment, if you start the walker in this region at the interface between the two magnetic field regions, you'll see that the walker will be confined along the y direction, along this edge. It will only transport itself along the edge, and it will actually and it will not leave this region, indicating that it's undergoing propagation through an edge state. You notice that the walker is going both left and right. The reason for this is because we are starting the walker in a single position at a single time, which means we're exciting this entire band structure. And as you can see, in some regions between Landau levels, you have a positive group velocity. In others, you have a negative group velocity, because we haven't done anything to restrict which part of the phase space we're exciting, because we've excited everything. You're going to see the cumulative effect of all of those different bands, and so you're going to see some of the particle walk to the left and some to the right, corresponding to these different transitions between the Landau levels. Okay, so that's a magnetic field. What about an electric field? Well, the way to create an electric field is by creating a time-varying gauge field. And in this case, it's very easy for us to do. We simply vary the gauge field that we apply in time. So we apply a linearly increasing phase shift at each time step. And if you have that, if you program that into the phase modulators, then what you expect is actually is transport with an electric field which produces a gapless Floquet band structure. So what do I mean by Floquet band structure? Well, in general, if we put any kind of phase shift here, there's no real well-defined band structure. But if the phase shift that we program is a rational fraction of pi, it turns out you can define a band structure, a Floquet band structure, which has a number of bands that is proportional to the 2 pi divided by the fraction of phases that you apply. And so here's an example of a 90-degree phase shift, which has 4 bands, because that 360 divided by 4 is 90. Here we have 60-degree phase shift, so 60 divided by 6, that gives us 6 bands. But you notice that these are all gapless. They all touch at Dirac points everywhere along the band structure. So we don't have a gapped structure here. What we can observe is a hallmark behavior of particle transport in an electric field, which is known as Bloch oscillation. So we start the particle at time 0 and allow it to propagate, and you'd expect under no magnetic field for the particle to ballistically diffuse. But sorry, under no electric field for the particle to ballistically diffuse. Once you apply an electric field, what you actually see is that the particle spreads and then reconverges back to the center. And then it'll keep doing that in an oscillatory way. This is known as Bloch oscillations, and we're able to reproduce these Bloch oscillations in 2 dimensions using this synthetic time-multiplexed space. Again, we can get more interesting. We can start to create all kinds of different materials that are not so easy to create using real space or using real materials. For example, in this particular case, we created something which I refer to as a synthetic quantum well. We have a region A, which has an electric field. We have a region B, which has no electric field. And we have a region C, which again has the same electric field. Now, it is really important to understand that even though we have electric fields, these are all gapless materials, and therefore this is not a gapped heterostructure. There are always states in this region that could jump to this region. However, because of the presence of the electric field, what we observe is basically confinement of the Walker due to basically the presence of the electric field. We're basically pushing the quantum Walker in between these 2 regions using the electric field. And so as you start the Walker in this quantum well region, it diffuses, but it then stays confined within this synthetic quantum well. This is a material that I don't think has been studied yet. Of course, it's kind of hypothetical because we're in a discrete space, a discrete random walking time. So it's a model that doesn't really correspond to any real physical materials, but it's an interesting model to think of as an analog for maybe some continuous time variance. And so it kind of gives you an example of how using these synthetic dimensions, we can play really interesting games with gauge fields and study things that would not be so easy to do if we had to actually make a real photonic structure that creates this kind of confinement. All right, so this part of the talk kind of gives you an idea of how we can solve this first problem of how to implement external forces. We can implement magnetic fields, we can implement electric fields, we can implement combinations of the 2. So now we have the tool to study photons with transport under gauge fields, but I have to admit that everything I've showed you so far is still only single particle transport, which means that technically I can just simply calculate theoretically what will happen. It's not a computationally hard problem to solve, and we can do the experiments in the lab, but they don't simulate anything that would be a quantum hard problem, because again we're confined to single particle transport, and the reason is because we lack particle interactions. This is the second really important missing ingredient. And so in order to get to this many body interaction regime, we need to go beyond single particle transport, and we need to find ways to engineer random walks with strong particle-particle interactions. And there are not many ways we know how to make single particle-particle interactions with single photons, because photons again lack mass and charge, and so they don't feel each other. The only way we can do it is to mediate the interactions using a two-level atom, and this is something that has been studied for a long time. The idea is that you take a two-level atom and put it in a cavity, and when the first photon comes in, it can excite the atom to the excited state, shutting off its absorption, and that will have an effect on the scattering properties of the second photon. And these effects can be, they can have different nature. For example, photon blockade, where one photon scattering off the cavity can prevent a second photon from entering the cavity. Or photon-mediated tunneling, another effect which actually encourages the second photon to enter the cavity once the first photon has interacted. And so these are two well-known examples of how a two-level system can mediate strong photon-photon interactions. And it's interesting to think about how to use them to do many photon simulations with interactions. And of course, the way you would want to do it is by creating large identical arrays of cavity atom systems, and then allowing photons to scatter through these large arrays, and in such a way that when multiple photons hit a single cavity at the same time, you get this strong photon-photon interaction. And these systems have been studied extensively in theory. There's been a lot of work on how to use them to study all kinds of different, all kinds of different behavior, including the realization of fractional quantum Hall physics, which was proposed by several groups recently, or actually not recently, quite a while ago. But the problem we have is that we simply do not know how to make large identical arrays of cavities. They are outside of our current technological capabilities because we just don't have the ability to reproducibly make many of them with exactly the same frequencies, exactly the same properties. There's all kinds of problems that put it beyond what we can currently do. So how do we get around this problem? Ideally, we can't make these arrays, but we can make, as I'll show later, good single atom cavity systems that perform well. So can we get away with just one of them? And the answer is we could if we, again, exploit synthetic dimensions. And so I remind you again of the one-dimensional random walk where we use only a single beam splitter, which uses two loops with slightly different lengths. And so this implements what I showed was the quantum Galton board. But it's completely linear because this beam splitter is a linear partitioner. If we replace that beam splitter with a nonlinear partitioner, basically an atom cavity system, now we can implement an equivalent random walk to this large array of cavities, but we can do it using only a single nonlinear atom cavity system. And the nice thing here is that we have these kinds of systems already, as I'll explain a little bit later in the talk. And so it now makes it possible for us to actually start to engineer interactions in these random walks with what we have to date. Okay, so but before we start to build this thing, we might want to ask the question, what does this kind of a random walk really look like? What would random walkers undergoing this interacting random walk, how would they behave? And this is a very difficult problem to solve because when you have two photons scattering off of a cavity, it creates a very large mixing of momentums between the photons. Even a single cavity, the original paper that studied it was a 16-page PRA, required a lot of math. And now we want to start to analyze not what happens when we scatter off one cavity, but where we successively scatter off many cavities sequentially, as is done in a random walk. And so in order to actually make this problem tractable, we created a formalism. Well, we didn't create it, we actually borrowed it, but we extended it. A formalism that was originally developed by Howard Carmichael long ago in the 1990s, called quantum trajectory theory. And Carmichael showed a very simple way to implement, to simulate how a cascaded scattering event of different quantum systems behave using a technique called projecting to the source. So instead of starting the particle here and seeing how it rattles down your system, you start at the source and then you basically go backwards to all of the different paths that could have contributed to it. And that significantly simplifies the computation. I won't go into the details because even though it's simpler, it's still quite complicated. And so I will spare you the details, and I'll go straight to the results of the simulation. But if you implement this random walk and you calculate it using this project to the source, then what you end up with is a very correlated random walk. So in this situation, we're simulating two photons that are starting at the center, and we allow it to propagate, in this particular case, 10 steps. And if they were uninteracting, they would just freely diffuse randomly. But in this particular situation, because of the interactions, they don't. They actually have very strong correlation. They walk together. If you have one photon at site X, the other photon is very likely to also be found at the same site. So these photons propagate as two photon bound states along the different positions of the random walker. They effectively attract each other. However, this is assuming that the photons arrive at the same time. If we tune the arrival times of the photons, and the way we would do this is by post-selecting the delay time between the arrival using single photon counters, we can actually change the nature of the interaction. In other words, so if we go from the situation where the photons arrive at the same time to the situation where they arrive at a delay of 1.6 lifetimes of the atom, we actually have the reverse situation. Instead of being correlated, they're anti-correlated. They repel each other. If a photon is found at position X, the other photon is more likely to be found at position -X. Finally, if we pick a very large delay, we reproduce the non-interacting regime where the photons are completely randomly partitioned in all directions. And this is kind of intuitive because once the delay between the two photons is very large, they're hitting the atom cavity system at completely different times, and so they don't interact with each other. So this is the case where we've actually used a detuning of the atom cavity system such that it achieves 50-50 beam splitting. We can also look at the case where we're resonant with the atom cavity system, in which case it behaves as a single atom mirror. And in this case, we also observe very strong correlations between the photons. Again, if we post-select cases where they arrive at the same time, we see this anti-correlated behavior. As we increase the time delay, what we find out is that the atoms progressively become trapped at the center. And this is again the case where this corresponds again to the case where there's no interactions, where the atoms are simply bouncing back and forth between the single atom mirrors. But if the interactions exist, they can actually mix with each other and form bound states that can escape the center. So once again, we're able to see that the interactions mediated by the strong nonlinearity of the cavity can result in very correlated photonic walks. So this is all computational. How do we actually implement this in the lab? Well, our group has for a long time been working with one particular type of atom cavity system, which are indium arsenide quantum dots and photonic crystals. These indium arsenide quantum dots are basically artificial atoms. They're small nanocrystals that are embedded in a semiconductor matrix. And they act very similar to, very close to a two-level atom. And if we place them inside of a cavity, we then have this this system that I showed earlier as a cartoon, basically a two-level atom strongly coupled to a cavity that can mediate strong photon-photon interactions. And there's been a lot of work on observing these strong photon-photon interactions, both the photon-induced tunneling and the photon blockade, using these semiconductor atom-like systems. And this is just a small subset of the papers that have demonstrated these kinds of nonlinearities, but there's still a big challenge that we have to face before we can just simply take the system, start to put it in delay loops and see this random walk, and that is that we we really have to get the efficiency very high in order to see anything. And you can imagine why that would be important. If our insertion loss into the cavity is 10%, then after 10 steps, we have to go in and out of the cavity 10 times. We have a probability of not losing the particle of 10 to the minus 10, which is extremely low, which basically means we're not going to see 10 steps. We'll never be able to see that many steps. And so in order to do a random walk with a reasonable number of steps, we have to push the efficiency, the total system efficiency, into the 20, 30, 40, 50 percentile. And that's the whole system efficiency, not just the efficiency of the insertion loss. It needs to include the generation rate of the photons, the detector losses. Everything has to be in the tens of percentiles. And that's actually the world record right now is about, I believe, 20% is the best anybody has ever done. That was a seminal work by Shanwei Pan's group in China. So this is a hard problem to solve. One of the things that we have been, the approach that we've been looking at is to use adiabatic tapering in order to create very high efficiency coupling to the device. The idea is to make a taper that is engineered to create a Gaussian-like far-field mode that has a transverse mode profile that we can match to a fiber through a lens system. And recently we have implemented this setup. From simulations, we expect 90% coupling efficiency into the far field. And we actually observed very high coupling. We observed in a pulsed excitation, we observed over 1.6 million counts per second of photon emission from this device using 40 megahertz excitation rate, which corresponds to an end-to-end efficiency of 4.1%. That sounds low, but it's actually one of the highest values that has been realized in telecom, but it's still not good enough. It's not good enough to do a random walk. We need to go even higher. And so we borrowed ideas from the Diamond Photonics groups. They have very effectively used adiabatic tapering to achieve very high efficiency into a tapered fiber through adiabatic coupling. Here you are tapering the nanobeam and reverse tapering the fiber so that the mode of the nanobeam adiabatically converts to the mode of the fiber, giving you a really smooth transition that can achieve extremely high coupling efficiencies, some as high as 97%, 98% reported in literature. So we implemented this technique, and from reflectivity measurements, we've observed coupling efficiencies into the tapered fiber as high as 60%. So that's starting to get much better. But we're starting to get into the regime now where you can actually do something, do a reasonable number of steps. But you got to remember, the 60% is just coupling in and out of the device. It's just coupling into the device. We have to also factor in all the other losses. So really, this is just a starting point. And in fact, we've also done this adiabatic tapering with cavities. So we've engineered nanobeam cavities with adiabatic tapering, and we've observed these very nice coupling efficiencies into the cavity. In this case, we're only getting about 50% instead of 60% efficiency. One thing that we're not doing so well in these particular cavities, we have relatively low quality factors. And we think it's something due partially to design and fabrication. We're still working on it, but these quality factors will have to improve in order for us to get good enough interactions to implement the random walk. But we're starting to get to the point where our devices are having a sufficiently high efficiency to make them interesting. And so this is kind of the next step for us, is to use these kind of cavity QED systems, adiabatically tapered fibers, so we can improve the efficiency and then start to realize these random walks by coupling a single quantum dot to the cavity. Now, so far I've been treating the quantum dot as a single two-level system. However, if we add an electron or a hole to the quantum dot, it can actually act as a qubit. The extra carrier in the charged quantum dot gives you a spin degree of freedom, which can couple to two optically excited states called triangles. And this gives us a means to optically control and measure spin in the quantum dot and do single qubit rotations. This is something that has been known and studied for a long time, with seminal work dating back to the group of Dan Gammon and Duncan Steele at Michigan, and also the Yamamoto group that did amazing work in this area. And so now we have the situation where we might, in addition to just having a simple two-level system coupled to these synthetic dimensions, we might actually be able to have a qubit. And what can you do with that? Well, what we showed a while ago, is that if instead of just using a two-level system, you use a qubit, you can actually engineer coherent interactions between the two photons. And this allows you to do optical switching and also allows you to build a photon transistor where many photons can collectively interact, mediated by this single spin. And so what can you do with that? Well, one of the things that we studied a while ago was applications of this kind of memory using time-multiplexing synthetic dimensions to implement quantum error correction in order to create one-way quantum repeaters. This was work that was a collaboration between my group and Jake Taylor's group. More recently, the Lucan group has considered what happens when you use these synthetic time-multiplex dimensions with a single qubit engineered in such a way that you create a two-dimensional cluster state. And if you can do that, you now have a path towards universal quantum computing. So if you can replace that two-level atom with actually a qubit that can interact with photons, you now have a route towards cluster state engineering. Our group has more recently looked at expanding this to higher dimensional cluster states, 3, 4, 5-dimensional cluster states. This is important because you need at least 3-dimensional cluster states in order to do fault-tolerant quantum computation. The nice thing about these approaches is that this can all be done with a single atom cavity system. We no longer need to have these very complex arrays of atom cavities that we just don't have today. We've also considered more recently we've proposed another way to use these systems to implement a quantum Fourier transform using synthetic dimensions with time-delayed feedback. So here, a single atom coupled system interacts with 2 time delays in order to take a sequence of n photons and spit out another sequence of photons that gives you the quantum Fourier transform. The really nice thing about this this idea is that it's an on-the-fly approach that does not require active feed-forward. And what I mean by that, in most photonic quantum algorithms, you need to be able to measure one photon and then apply a unitary operation on the other photons conditioned on the measurement result. This is called active feed-forward. And it's very hard to do because you need to be able to store the photons in some sort of memory so that you have time to make the measurement and then go back and implement the desired transformation. Here, you don't need to do that. It's an on-the-fly approach. N photons go in, N photons come out, and you get the quantum Fourier transform. You never have to do this active feed-forward to conditionally change the unitaries you apply based on what the photon measurement was. And we showed that using this approach, you can, with reasonably achievable cavity QED parameters, implement quantum Fourier transforms on tens of photons. So one can foreseeably do some interesting experiments. Of course, if you really want to make this scalable, you need to be able to introduce some sort of quantum error correction here. This is something we haven't done yet. It's an area of future work. So, in conclusion, I want to thank all the people that have contributed to this work. My group, who has really did all the experiments that you saw. because of COVID, my picture is so incredibly out of date that in fact the majority of the work that you saw today was not, none of the people that did that work are in this picture, because it's been so long since we've been able to sit together like this. So I need an updated picture. But I do want to thank my group members, particularly Changmin Lee, who did a lot of the experimental work, and Hamid Reza Chalabi and Jinwan Zheng, who did a lot of the interacting walks in synthetic dimensions, and also the gauge fields in time-multiplexed synthetic dimensions. Our collaborators who who did all of our MBE growths for our experiments, as well as Mark Morris and Jerry Baumgartner, our collaborators at LTS, and our funding agents. And most importantly, I want to thank you, the audience, for participating and listening. And without any further ado, I will open up the floor for questions.
Thank you, Edo, for that wonderful talk. I have some questions. There's a couple of questions in the chat, and I'm encouraging now is a great time for audience members to put in a few more questions. We have time for some questions. Maybe to start off, I'll ask one of my own, which is, what are the requirements for the atom cavity system for cluster state generation, and what are the most promising systems for realizing these requirements?
Yeah, it's a really good question. We actually did a very extensive analysis of this in, hang on a second, let me, sorry. So in this paper, we actually do a very extensive analysis of this. And so there's a few things that you need. First is high cooperativity, but the cooperativities don't have to be very high. They don't have to be 1,000. Cooperativities of tens are quite good. The second thing you obviously need is a very low insertion loss, because no matter what you're doing, you know, if you have n photons, if your efficiency is eta to the n, right? So obviously you need very high insertion loss. But one surprising thing that came out of this analysis that we didn't know before is that there's another requirement that we didn't anticipate, and that is that there are two ways in which you can create these interactions. One is to actually apply a very large magnetic field and use Zeeman splitting, so that one transition is tuned to the cavity and one is detuned. And this is the way that we've done it in the past, and it's the easiest way to do it. And that way, if you do it, requires impractically high magnetic fields, and it's a fundamental problem. There's no way around it. The other way is to use chiral coupling, which deterministically couples one spin transition to one state and one other spin transition to another state. And that makes it that you could, it eliminates the need for the large magnetic field. You can actually work at magnetic field degeneracy. And so one of the things we discovered in this analysis is that you need this chiral coupling if you want to practically implement this. And that's something, I don't know if anybody's really done that very well yet. And so it's something to know. If you really want to do this well, chiral coupling, you need your cavity to be chirally coupled, which means you need one transition coupled to one mode and another transition coupled to another mode through circular polarization transitions.
Okay, thank you. One question from Arca: for the topological quantum simulators, do you really need to go to the blockade regime, or even classical switching, average photon number less than 1 exists fine?
Do you need to go to the block? Oh, I didn't. Oh, I see. I guess Arca, I'm assuming what you're asking is not the blockade regime, because some people call recoupling nonlinearity photon blockade. I'm assuming you're asking strong coupling, whether you really need strong coupling or can you just work with high cooperativities. And the answer is you can work with just high cooperativities. And most of our simulations assume you just need high cooperativity. We have not actually analyzed the situation in which you go into the strong coupling regime and use photon blockade. In fact, all of our computations use the 1D atom approximation where you're in the weak coupling regime. So it's interesting to ask what would happen if you went to strong coupling and whether that would yield different interactions in your random walk.
Okay, and then another question, in the coupled cavity array, the coupling generally nearest neighbor, will synthetic dimensions allow you to create arbitrary coupling?
That's a good question, and it's a tricky question. So the answer is you could, if you put active amplitude and phase modulators. So we're actually looking into this in the context of implementing SSH models, where you, for example, couple to the left more strongly than you couple to the right. And it's a bit tricky. You actually need amplitude modulators or tunable beam splitters in order to do that. But it can be done if you have that.
How fast? This is my follow-up. How fast would they have to operate at?
They would have to operate faster than the arrival time. So if you the time delay between the pulses, and so that ultimately corresponds. You have a short delay and a long delay, and so you have to, the difference between those times is the speed with which you have to modulate the amplitude modulator. And in our case, that corresponds to about 5 to 10 nanoseconds. If you go to bigger fiber loops with bigger delays, you can go slower, but of course, other things start to become problematic.
Okay, maybe some more technical questions on some slides earlier. One thing that you mentioned very early in the talk on the Landau-like band structure. Mm-hmm. You showed a picture that you said showed that this is just ballistic diffusion. This was in the absence of the magnetic field. What does ballistic diffusion mean? And what are we actually looking at step 9, which kind of looks like a blob that has two sharp points, but you actually see detection in an entire circle?
Yeah, that's a good question, and I went over this kind of quickly and didn't elaborate well enough. Ballistic diffusion means that if you look at the variance as a function of time, it would be linearly increasing, which in this case, if you just took the variance of that, you would see that it's linearly increasing. That's one definition of ballistic diffusion. And so the shape itself is a little weird, but the variance has this linear behavior. Whereas here, if you looked at the variance as a function of time, you would find that it's sublinear. It's actually kind of slopes off. And so that's how we differentiate between ballistic and non-ballistic diffusion. I should have probably explained it better. It's explained better in the manuscript. I didn't show those plots here, but that's how we differentiate between the two.
Okay, great. I think that we are just about at time. So I want to thank you again, Edo, for sharing these wonderful results and sharing your time with us. This video will be available after the talk through the same Teams link indefinitely. And yeah, thank you so much. I do think we have a closing slide that we can put up, but it was a great talk, and thanks. All right.
Thank you for inviting me.